have a look at page 30, November 2016 P21. Okay. I think it's the page before the one or two pages before the current question that you were doing just now. Okay, it's I think one or two pages before the question that you just did, right? Okay, so look at page 30, define potential difference. Okay, so this one here, they just ask you to define electrical potential difference. This is actually just a general definition. Okay, so in your case here, you will just write it as electrical energy converted to other forms of energy per unit charge between 2 points in the circuit. Just follow the definition inside the notes. But if they ask you about, say, PD, define PD of a resistor, where they specifically mention to you what component is it, then you cannot use back this same definition that you just wrote. You have to say it is electrical energy to thermal energy or heat energy. Okay, maybe I just write heat energy. Okay, so electrical energy to heat energy per unit charge. Okay, so if they specifically mention to you to define the PD of a resistor, you have to be specific on the type of energies that has been converted. You will say it's electrical energy to heat energy per unit charge. But since your current question here didn't really mention anything, what component is it for, they're just asking for you PD in general, just give a general definition. You would just write electrical energy converted to other forms of energy per unit charge between 2 points in a circuit. That's all that you need to do. All right. Okay, then look at part B. They ask you a battery of EMF 14 volts and negligible internal resistance now connected to a network of resistors. R1 and R2 are fixed resistors of resistances 6 ohm and 12 ohms respectively. R3 is a variable resistor. Switch S is closed. Okay, they tell you switch S is closed. Calculate the current in the battery when the resistance R3 is set at 0. Okay, so this question here has something to do with short circuit. The first part here already has a question related to short circuit. So they tell you that the switch S is closed and then R3 is set to 0 ohm. Okay, so your circuit, if I want to draw it out, would now look like this. This is 14 volts. This one is R1 at 6 ohm. Then this one is R2 at 12 ohms. And then this one here is R3 at 0 ohms. Switch S by right is closed, so nothing to it there. Okay, now of interest to you is this portion here, where they tell you resistance is 0 right now. This part here will be your short circuit. This part here is your short circuit. You now have a short circuit inside your circuit. If you watch the other recorded lesson before this, the latest one that I asked you to watch, the beginning of that lesson, I mentioned, I went through what was short circuit. So short circuit is when you notice that there's a path of 0 resistance inside the circuit. So if you notice there's a path of 0 resistance inside the circuit, the current, all the current inside the circuit will just flow through that path instead. Okay, without splitting up at the junction. So you have something similar right now in the question that you're seeing. This red colored path that I highlighted to you is your short circuit because it has 0 resistance. It's your short circuit path. It has 0 resistance. So what will happen is that if I were to draw out the current flow for you, current will go out here. This is current I. It flows like this. it flows through R1, and then it reaches this junction. So by right, you know that this current can actually split here, it can actually split here, right? But because this path at the bottom, the red colored highlighted path, has zero resistance, what will happen is that current actually won't split out to go to the top path and bottom path. All of them will instead go to the bottom path. That is what short circuit actually is. The moment you have a path of zero resistance, all the current will just flow through that path without splitting up at the junction. So the current reaches this junction, all of them will just flow through this red color path here. And then it goes like this back into your battery. So this path here, I will highlight as blue. This one has no current flow. Okay, so this one has no current flow through to the short circuit. Okay, this is how you will see your circuit right now. Okay, so this is like this. So they want you to calculate the current in the battery when the resistance is set to 0. So what you can just do is that from here, you apply Kirchhoff's second law. Okay, if you apply Kirchhoff's second law, maybe I need to use a different color. What color should I use? Okay, now I use light green. If you apply Kirchhoff's second law for a loop, you apply for this portion here, the part where that includes the short circuit path. In other words, just include the path where you have current. Okay, so you apply Kirchhoff's second law for that path there, where we tell you sum of EMF is equals to sum of PD. EMF E is equals to V1 only. Okay, right? You see, my EMF is this one, my PD is this one, V1, and then this one, although there's a resistor there, but the resistance is 0. Okay, although there's a resistor R3 there, there's actually no PD across it because the resistance is set at 0. This one has no PD. So R2 I don't even need to consider because it's not part of my loop also in the first place. Okay, so E is equals to V1. V1 is actually current I times resistance R1. So you know the EMF as 14. Your current is what you want to find. Your resistance R1 is 6. So your current is 2.33 amps. Okay, so that's one way how you want to do this question. Okay, just recognize that you have a short circuit here. All right, so now you have already done this part 1. What about the next part where they suddenly tell you now R3 is set such that the resistance is going to be 24 ohms. Okay, so now you set your resistance at 24 ohms. The equivalent circuit will now look like this. The first one is something like this. This one is 6 ohm. This one is like this. You know, this one is like this. This one is R1. This one is R2. 12 ohms. This one is R3. 24 ohms right now. Okay, so let me just get this sorted out. Okay, so now you have a case where the resistance R3 actually has some value of resistance there. It's not 0, so you don't have any short circuit now. So now what you can do is that they want you again to calculate the current inside the battery. All right. So how do you go about in doing that? You can actually simplify this circuit into an equivalent circuit. Basically, you want to simplify this one such that you get this. This one is still R1, 6 ohm. This one is your resistance in parallel, giving you this. Okay, you simplify the parallel connection to a parallel resistance. Okay, then after that you get this. Okay, so to find out what is the parallel resistance R parallel here is just 1 over R parallel, 1 over R2 plus 1 over R3 is 1 over 12 plus 1 over 24. Just multiply with power negative 1. You're going to get the answer as 8 ohms. Okay, so this one you're going to get 8 ohms. So same thing as before now, you want to kind of apply Kirchhoff's second law here. Or actually you don't need to lah. What I did here was that I simplify even more so that this circuit is now like this. Because these are resistors in parallel, in series, you see, I can actually just add them out. This one will become 6 plus 8 becomes 14 ohms. Okay, so I simplify all the way to the max. I want to find the current I now. So I apply sum of EMF equals to sum of PD. This is E equals to I times R total. So is 14 equals to I plus with 14. You're going to get your answer as 1 ohm. Okay. Now you can also do from here also actually if you wanted to. It doesn't matter which one you want to use. It's dependent on specific people. I can also just say sum of EMF equals to sum of PD. E is equals to V1 plus the voltage across the parallel connection. So E is IR1 plus I times R parallel, where this one is IR1 plus R parallel E. So you will get back this answer. Okay. So it doesn't matter which one you want to use. Just use the one that you're most comfortable with. Just follow the same proper rules and you should be fine. Okay, so you get the answer as 1 ohm. 1 ampere. Yeah, another thing I should probably mention to you here is that when you do your calculation, your calculator will just give you 1. This one is 1 SF only. So don't write your answer in 1 SF. Write your answer as 1.0, so that is 2 SF. This one is correct. I mentioned to you guys before a number of times, final answer minimum 2 SF. Maximum 3 SF. So maybe I should just write it carefully. Minimum 2 SF, maximum 3 SF for final answer. Okay, so just bear that in mind. All right, then after that, the next part is already a bit different. Okay, right. So look at the next part. They say use your answer in B1 to calculate the change in total power produced by the battery when the resistance R3 is changed from 0 to 24 ohms. Okay. They want the thing here to be this. Wait, let me just clear off everything. I'll just clear off everything here. They want to find the change in total power produced by the battery. Okay, keyword total power produced by the battery. The thing that should come to mind is power of battery is EI. Okay, so what is the change in total power produced by the battery when your resistance R3 was changed from 0 to 24 ohms? So basically what you just want to do is that your change in P is basically E I2 minus E I1 or E, yeah, just take either one. Okay. If you take, yeah, so your power is just this one, the change in power is just this. You take 14 volts, multiply with one of your current 2.33 minus with 14 volts, multiply with your other current 1 amps. You're going to get 18.6 watts. This one is the most straightforward one. Power produced by battery. Just use EI. Okay, so use that and you should be okay. All right. Just take whichever value is higher minus the lower. If you are taking I2 as 1.0 and I1 was 2.33, you're going to get a negative answer, right? So don't bother about that. Just take whichever value is higher minus the lower one, or like what I've done here. Okay. Just take the higher value minus the lower value. Don't bother about which one should be minusing this, which one, because you want the change in value only. So if we're not really that particular about whether it's I2 minus I1 or I1 minus I2, just take whichever is higher minus the lower. Okay. Maybe I just write this now. Take higher power minus lower power. Okay, and you'll be done. Okay, so this one is okay. Then after that, we go through part C. Okay. Part C is some other changes that are made to the circuit. Now they tell you switch S in figure 6.1 is now open. Okay, before this, the switch was closed. Resistors R1, R2 are made of the same metal wire. Some data for the three resistors are shown in this figure. Find out the ratio average street speed of electrons in R1 to R2. So it helps to always try and draw a little diagram to help you visualize what's happening. Okay, so if my switch S is open right now, I have something like this right now. I have to redraw this again. This one is open. This one is R1, 6 ohm. This one is R2, 12 ohms. This one is R3, 0 to 24 ohms now. Okay, so my switch S is open. Once your switch S is open, you try to look at how your current flows. Current will flow like this, like this, like this. And then after that, it reaches this junction. Now, this part here is broken. This one is broken connection. Okay, is open. All right. Current, once it reaches that little junction there, because the pink colored highlighted part is a broken connection, is open, current won't flow through here. Okay. It will just go like this, and like this. Your current flow is this blue colored section here. Okay. So you flow through that in this manner, here like this. So the question is asking you to find out what is the ratio of the drift speeds for resistors R1 to R2. Okay, so they want you to find out the drift speeds for resistors R1 to R2. So the moment you hear mention of drift speed, there's really only one equation that you will ever use. That one is your drift speed equation, which is I is equals to ANQV. All right. Now there are a few things that will be constant here. You're talking about electrons. The charge of electron is always 1.6 times 10 power minus 19. Okay. And then you look at your diagram that you just drawn here. The current that flows through R1 is the same as the current that flows through R2. So I is constant here. I can say that I and Q are constant. So drift speed is actually inversely proportional to area times my number density. Okay. So right now, I want to find out what is my drift speed. I actually made this even more complicated than it's supposed to be. This one, I'd rather you don't write it like the way I did. I'd rather you write it like this now. This one, you can say that since V is inversely proportional to area times number density, you can just write it as this. V1 to V2 is the same as 1 over A1 N1, 1 over A2 N2. So therefore, it gives you A2, N2, A1, and 1. Okay, this will make your working a whole lot easier. So you just sum in everything that you know. A2 is 0.8A, N2 is 0.5N, so this one is AN. You just sum everything in, you're going to get the answer as 0.9. Okay, so there you have it. Right, so your answer is this. Okay, so yeah, another thing before I end this question, just be mindful. Just now, the earlier one, the other example that the first part of your question here, we had this one here like this, where the switch was closed. Yeah, the switch was closed, but then after that we said that this R3 here was 0 ohm. So when current was flowing, it went like this, reached this junction, it went all the way down before going here like this, right? Then this part here, I mentioned that this one was short circuit. This part here is your short circuit. So current will flow like this only. And then this one I said that this part here I mentioned no current flow. Okay. So you see, under both cases, there were junctions here, but then after that, the current never split. All right, the current just went to fully go through one path only. Okay, but the reasons why they did that are entirely different. In the first case that you had, it was because this one was short circuit, so current all decided to go through here instead. In the last case, you have this second case here, current did not go through here, but instead it went through here. That's because this one is a broken connection. Okay, so just be careful about the differences. Sometimes current will only flow in one path only without splitting out, either because the path that is taking is a short circuit, or either because the other path that it can choose to take is broken in the first place, so it won't take that path. It instead goes through the other path that is closed. Okay, so just be careful about that. There's actually some differences there. Okay, so this one is okay. Then we go through one MCQ question that relates to short circuit. Then after that, I move on to something a bit different. Is it page 10? Oh yeah. Okay, so I'll just clear all the drawings that you have here. Okay, have a look at page 10. Okay, page 10, question 35. This one has something to do with short circuit also. Okay, it has something to do with short circuit also. It wants you to look at how to deduce certain things. Okay, right. So look at this question. They tell you 110 volt DC supply is connected to a heater, a fuse, and a switch. Owing to a fault in the system, power is now not supplied to the heater. A technician diagnoses the fault using a voltmeter. He closes the switch and connects his meter between the positive supply terminal S plus and the fuse terminal F2. The voltmeter now reaches 110 volts. Which of the following diagnosis is correct? Meaning to say which of these following faults is correct that give you these observations over here. Okay. They're asking you which of these answer choices is the correct fault that gives you this observation where you get a voltmeter reading of 110 volts. Okay. So this one, I think I better just refer to a diagram that I did before. November 15 P11. So let me just open it up. Okay, November 15 P11 will be this one. Oh, I have that diagram code, right? Okay, no, I didn't draw it correctly here. I must have drawn it in a different diagram. All right, never mind. Let me just do this one. I see this for you. Okay, so to do this question, you have to kind of like draw out the circuit that is being described by each of the following faults. Okay, so let's just look at this one in the first place. Okay, let's just say that right now I look at fuse has melted. Okay, I look at the part where fuse has melted. The circuit will look like this right now. This one would be S plus, S minus. This one was your fuse. Okay, and then this one, your switch is closed. This one is your heater, like this. Okay, so if let's just say we assume right now this is what's happening for, if you look at section A itself, where we say that the fuse has melted. So when we say that the fuse has melted, let's assume that the switch is closed, the heater is here, and this is your fuse. When they say the fuse has melted, that means this one has melted. This one means you have a broken connection. Okay, broken connection, current no longer can flow through. Okay, the fuse has melted, current can no longer flow through. There's actually no current in system. Okay, because you cannot form a closed circuit here. All right, but then after that, you now have to look at the variation in potential. Okay, now I see your question told you that you have 110 volts here. This one, they tell you it is 110 volts across your power supply. 110 volts across your power supply. What this could mean is this. From here to here, you're having 110 volts potential. But from, what color can I use? Yellow. Right? But from here to here, this one is 0 volts potential. Okay, remember I told you before in 1 or 2 lessons before this, the value of electrical potential actually won't change unless you have your charge has passed through a battery where it gains electrical energy, so your electrical potential increase, or if it passes through a resistor where it starts to lose electrical energy, so its electrical potential decrease. So in my case here, there's actually no charge flowing. No charge flowing through battery, no charge flowing through resistor. By right, there shouldn't be any changes in potential. Okay, but I have a power supply here whose PD is 110 volts. So one end must be, the difference between these 2 points must be 110. So I can say that the green color section that I just highlighted would be having a potential of 110 volts, but the yellow color section that I just highlighted will be having a potential of 0 volts. So that the difference between these 2 points is going to give me 110 volts. Okay. So you look at what the question described, they tell you the technician connects his voltmeter, he closed the switch already. He connects his voltmeter between positive supply terminal S plus and fuse terminal F2. This one, S plus and F2. This is where he connects his voltmeter. So now, if this one was S plus, and then this one here is F2, okay, your you can try to imagine if you have a voltmeter connected between these 2 points, right? Between here and here. Now this one is at 0 volts potential because it's connected to the yellow colored line. This one is going to be 110 volts potential because it's connected to the green colored line. So the difference in potential between these 2 points will give me 110 volts, no? So this is actually supposed to be the correct diagnosis. Your fuse has actually melted. That's why I'm getting 110 volts when I go and connect my circuit like that. Okay, but we can also try and do the other sections, the other parts, just to see what could be the differences. Now, if I look at part 2, sorry, not part 2, part B, where I tell you fuse has not melted and there is short circuit in heater. Okay, how does this change everything? Right, so what you can then do is, again, you try to redraw the same circuit. This one is S plus, S minus, same circuit, but you have the heater here, 1, 2, 3, like this. And then this one is basically your fuse. This part here is your F2, all right? And then they tell you have a short circuit. Now, this one, they tell you have a short circuit. You can just imagine right now, when you have a short circuit inside your heater, there could be a bare wire bypassing your heater. Okay, this one is, you can just think of this as a bare wire bypassing your heater. All right. So in your case here, there is current flow. There is current flow because you can make a complete circuit here. This is a closed circuit. Current can flow. So what you can say is that current flows like this, it flows like this, it flows like this, it flows like this. But then once it reaches here, you see, you can have two paths to flow. Either you flow this way or either you flow this way. But you see, your heater by right should have resistance, but your bare wire has no resistance because the question already says it's a short circuit. So once your current reaches the junction before your heater, it won't flow through the heater. Instead, it flows through the bare wire. It flows through the short circuit path. Okay, so your current flows through the short circuit path. It goes like this right now. Okay, so maybe I should just highlight this. This one is your short circuit. This part is your short circuit. All right. Okay, then after that, let's just look at the changes in your potential. Now, your fuse, if current flows through it, it has no PD. Okay, it is assumed to have no resistance. This is one thing that we should kind of get sorted out. If there's current flowing through your fuse, there is no PD across it because it is assumed to have no resistance. Okay, so right now, if I just want to look at my circuit right now, and I see that this one is say 110 volts across my power supply, there is actually no way where I can have changes in electrical potential. There's no way that my current purposely flow where there is changes in electrical potential. So what I can say from here is basically this. I can kind of think of it as this entire thing here like this is just going to be 110 volts potential. Yeah, I can just think of it as just like that, 110 volts potential. There's no difference in potential anywhere in the circuit. there's no PD anywhere in the circuit because it did not go through any resistance. So right now, if I were to connect a voltmeter between S1, say S plus, and F2, this one here is 110 volts potential. This part here is also 110 volts potential. You're going to end up with 0. So B is out. Okay, so this one is this. Okay, then we go on to C. How do we go and see for C? You know, this question is a bit long and tedious. Okay, now let's look for C. Okay, I'm just going to use some short form here. For C, 3 is for C. For answer C, I don't want to reproduce the same writing again. So they tell you the fuse has not melted and there's no path for the current through the heater. Okay, so this one will now look like this. I redraw it S plus, S minus, like this, like this. This is my fuse. This is my point F2. Now they say there's no path for current inside the heater. This one can actually mean this. There is broken connection in heater. So there's a broken connection here. Okay, there's a broken connection in your heater. So the conclusion you can come true is that because there's a broken connection here, no current in system, because it cannot flow out from this end and come back to this end in one complete loop. So no current. Okay. Now from here, if you just look at the potentials again, I know that this one here is 110 volts, the EMF or the PD. But if I just look at the values of potential here all the way to here, this one will just be 110 volts. Potential. But then here, go to here, this one will be 0 volts potential. So if my voltmeter is connected from S plus to F2 here, this one is 110 volts potential. This one is 110 volts potential. Obviously, this one will be 0. So I'm not getting 110 also. C is out. Okay, so that's how you look at this one. Okay, last one. The fuse has not melted and the switch has operated correctly. Okay, so this one, fourth one, doesn't seem like there's any issues with this. No problems, no error. So let's just say you see for answer D, I try to redraw the same thing again. This is S plus, this is S minus. You have that same circuit here. Everything is working fine. Okay, so this one got current flow. Current flows like this, like this, like this, like this. No breakage whatsoever, no short circuit whatsoever. So the thing here is that if I tell you that this one here is 110 volts, your EMF line, if you have to. This one here, because your current is now flowing properly through your heater has resistance, it's going to lose, it's going to have PD. So according to Kirchhoff's second law, if this one is EMF 110 volts, this one should have 110 volts PD. Okay. So now I want to look at the variation in my potential right now. So variation in my potential here to here to here is going to be 110 volts potential. But then from here all the way to here, it is 0 volts potential. Now it's because this one is 110 volts potential and this one is 0 volts potential that you get a difference in potential of 110 here. Okay, this is reasonable. So now next thing, you want to connect your voltmeter between S plus and F2. So you can see here, this is 110 volts potential. This one is 110 volts potential. There's no difference in potential difference between, there's no difference in potential between these 2 points. So your potential difference is 0. So D is out. So the only correct one is A. Okay, right? So this is how we look at this diagram. Okay, so it has something to do with short circuit also now. So the short circuit one was actually part B. All right. Okay, so this one is okay. It's been a long question, so we just do something a bit easier now. Okay, so this one is okay. I just go through another different question. This one involves you summing EMF. This is another different part that most people have issues with. So let's look at page 49. Okay. So I'm just going to clear up this diagram. If you want some time to copy, you can refer back to the recorded lesson later. All right. Okay, so look at page 49. November 17 P21. Okay, one of the things also that you will need to be careful of in your questions in DC circuits is when it comes to summing PDs and EMF. You will notice quite a number of questions on that. All right, so now you have 3 cells of EMF. This one is page 49. Okay, probably by the time we finish this, it's almost time already. Okay, so 3 cells of EMF E1, E2, E3 are connected into a circuit as shown. The circuit contains resistors of resistances R1, R2, R3, R4. Currents in different parts of the circuit are I1, I2, I3. The cells have negligible internal resistance. Use Kirchhoff's law to state the equation relating the currents I1, I2, I3. Okay, so when it just concerns the current, this one you can easily just use Kirchhoff's first law. All right. So Kirchhoff's first law is total current entering junction is equals to total current leaving junction. If you think this is a handful to write, you can just write it as this. Sum of current in is equals to sum of current out of a junction. So I2, I1, I3, I1, I2, I3. So which junction do you want to pick? You always have to pick a junction when it comes to summing up, when it comes to evaluating Kirchhoff's first law, you always have to pick a reference junction. So in your case, this one is a good reference junction. This is the junction you want to look at. So sum of current going into a junction must be the same as current going out of a junction. If you look at Y being your reference junction, I1 is going out of your junction, and so is I2. But I3, as it flows, is going into your junction. So the expression should be I3 equals to I1 plus I2. Okay, this is how you can easily try and see Kirchhoff's first law. All right. Okay, then the next one, they ask you to find out the E1, E2, R1, R2, R3, I4, I1, I3 in the loop W, X, Y, Z, W. Okay, so this one I'll have to rub off whatever I have here. So they want you to sum out those EMF and PD in loop W, X, Y, Z, W. That one will be this one, W, X, Y, Z, W. Okay. So this one is going in this direction like this, based on what the question just described to you lah, right? You're kind of like, this is your sign convention right now, clockwise. Okay, so from K2 law, this one is K1 law. From K2 law, which tells you sum of EMF is equals to sum of PD, right? You will have to start summing out your EMF. What are your EMFs here? This one I'll circle in blue. From this orange colored loop, what are your EMFs? This one is IE1. This one is I3. Okay, so how you sum up EMF in PD, that one was actually explained in one of the lesson recordings for DC circuits. I think it's the first one. That one I explained page 3, how you actually sum up your EMF and how you actually sum up your PD. So for PD as well EMF, I mentioned to you, you always look at the positive terminal of your EMF. What is the direction where current is supposed to flow out from? In your case, for the EMF, the red color arrow indicates the direction in which current is supposed to flow out from. So notice this one is going counterclockwise. Sorry, this one is going clockwise. This one is going clockwise also. So this one, E1 will be positive. E3 would be positive. It's pushing current in the same direction as your sign convention. So E1 plus E3. There's no negative here. Okay, E1 plus E3, there's no negative here. And then after that, what you want to do is this. You want to sum up your PDs. Okay, so when you want to sum up your PD, I mentioned that you have to look at the direction of the current flowing through your resistors. So the resistors, I will circle it for you. There are 3 resistors, R4, R1, and R3. So you look at the direction of the current flowing through the resistors. If you don't have a current direction indicated in the diagram, you have to assume one, okay? But there are cases where the question already would have indicated to you the direction of the current flowing through the resistors. So you see, in my case, I know I3 will continue flowing here. They already indicated the current I3 in your diagram. I3, it will continue to flow through your R4 here. Okay, so I3 goes this way. And then you notice that I1, which is indicated in your diagram, will flow through your R1. So this one is also indicated. Then after that, you look at your I3 again. Just now I shifted it forward. You can see it flows through I3 here. If I shift it backwards, you can see that I3 will also flow through R3 in this direction. Okay. So you then again try and look at the direction. If you just look at R3 itself, maybe I'll use pink. The current I3 through R3 has a tendency to flow like this, clockwise. So this one is going to be positive. The current I3 through R4 also has a tendency to flow clockwise. So this one is going to be positive. The current I1 through R1 also has a tendency to flow clockwise. So this is going to be positive. So all in all, you can say that I1 R1 plus I3 R3 plus I3 R4. That's what you're going to get here. Okay. Yeah, there's a typo error here. This one I'll have to correct it later. So just to be mindful of that. It's page 49. Okay, so that one is this not supposed to be I1, it's supposed to be E1. My mistake here. Right, so this one is summing out your EMF and PD. Okay, now what about for loop YZWY? So let me just clear off the drawing here. Okay, loop the YZWY, I'll clear off the drawing. All right. Okay, so for loop YZWY, okay, maybe I better not do that. Oh, sorry, let me just undo. Okay, so the next one they say for loop YZWY, let's go with this one. They say loop YZWY, that one would be this one, from Y to Z to W to Y. You can just think of your direction as being clockwise again now. Okay, this one is your sign convention. Okay, so single out your EMF, this one and this one. look at the direction of the current flowing out from the battery. Look at the positive terminal because that is where the current by right should be flowing out from. This one, E1 is trying to push current like this. E2 is trying to push current like this. Okay, but you see this one, E1 is trying to push current clockwise, following your sign convention, so this is positive. But E2 is trying to push current counterclockwise, opposite to your sign convention, so this one is negative. So for the second section here, you would say that E1 minus E2. Okay. Your negative here for E2 is mainly due to the fact that it's trying to push current opposite to your sign convention. Okay, so that one is all right. And then after that, you look at your sources or PD, which are your resistors. You have R1 and you have R2. Okay, so try and look whether there's any existing current flowing through your resistor indicated by the diagram. If there isn't, then you have to assume one. So luckily for you, the diagram already indicated to you. So current I2 actually flows through R2. It's trying to move counterclockwise. So this one is negative. For R1, you have current I1 flowing through R1. This one is trying to move clockwise. So this one is going to be positive. So all in all, you're going to get I1 R1 minus I2 R2, which is what you're getting here. Okay, so this is how you sum up your EMF and PD.